In this video, we look at one of the example problems from section 13.1, and we'll look specifically at like problem number, which one were we going to do? 30, there you go, 29. Okay, so take a moment to write down problem number 29, section 13.1, 29, and we are trying to find the points, the values of t, so that the tangent line to the given curve, so you have a given curve r of t, and it's given to you as 2t, t squared, negative t squared. Okay, and we need to find the tangent line and find the time so that the tangent line contains the point p is equal to 0, negative 4, 4. Okay, so we're looking at the point. Okay, there's our problem. Okay, we've been given a curve and we want to find a point, and the directions were to find the time such that the tangent line is at the point P at this time. Okay, so maybe just a sketch to even figure out what this question is asking. Okay, dimensionality wise, we're in three-dimensional space. Okay, we have a curve that was given, r of t. Okay, and there's a point P in this problem. Point P is out here. Okay, and at some point you're going to find a tangent line. Okay, a tangent line. Okay, and this tangent line, okay, needs to intersect the point P. Okay, find the values of t so that the tangent line to the given curve contains the given point. Okay, there is our problem. Okay, interesting. Okay, think we're looking for, at some point along this curve we have a tangent line, and we're supposed to, this tangent line is supposed to contain the given point. So this point P will be on this tangent line at some point. Okay? Alright. Not sure exactly how to do this, so let's just kind of jump into it. Okay? I mean, a couple things that you can always be thinking about. Notice that if you're keeping track of the Mathematica stuff, if you go to our website, okay, go to the course links, go to Calculus 3, and you download these Mathematica examples, okay, that'll bring you to this document, okay, and then you can click on, maybe the, just to plot a vector valued function. If we click on that one and we put in the curve that we're interested in here, which is 2 times t for x, t squared. Now I'm kind of stalling at this point, to be honest, so I can try to think about this problem. But when this is very typical, if you get a problem, just trying to do some small steps to get organized here. Okay. So there's our curve. It's some curve in three-dimensional space. And, well, if you plot it for less time, okay, we're getting this curve. Okay. And there's a point 0 in the x. 0 in the x direction. So there's our x-axis, y and z. 0 in the x, negative 4 in the y, and 4 in the z. Okay, we're trying to find the point on the curve that if we draw a tangent line, our tangent line to this curve will go through this point. Okay, so that's the question. I'm not sure the graph really helps, but let's see what we can do over here. Okay, we have a curve that's given. Okay, we can go ahead and find r prime of t. Right, we can find r prime of t. And this will give us the direction vector. It will be 2t, negative 2t squared. I'm sorry, negative 2t. Okay, so there's the derivative, r prime of t. This will basically give you the direction vector for the tangent line at any value of t. Okay? So, let's see what we can see here. Is it possible that when we draw our tangent line will be a function of some other variable s? Okay, that's our one variable s. This is, quote, the time along the line. Okay, it's going to be a line that goes through the point given. Okay, so this is your point P. The direction vector of the line is your direction vector v multiplied by the time s. Okay, so let's see what we can say here. We'll have a line. Okay, and this will be the tangent line at any particular time given will be L of s is equal to r of t plus r prime of t times s. S being once you start moving along that line, how long you're going to go for. That's s. And t is at what point you are along the original curve. So, L of s would be the curve r of t, which was 2t, t squared, negative t squared, okay, plus the direction vector 2, 2t, negative 2t, multiplied by s. Okay, and this line should equal, the question is, if you move along this line, okay, does the line L of s, which is 2t plus 2s, comma t squared plus 2ts, just adding these two vectors, I'm distributing the s through and adding the two vectors, so I'll get negative t squared minus 2t times s. And the question is, does this line equal to the point P, 0, negative 4, 4? Can that ever be true? Okay, so it looks like we have a system of equations to solve. System of equations. And now we have 3 equations, but 2 unknowns. And the unknowns are t and s. So I'm hoping something happens here. I'm not sure what's going to happen. So we need 2t plus 2s has to equal to 0. T squared plus 2t times s has to equal negative 4. And negative t squared plus 2ts has to equal 4. Okay. This equation is nice. It tells you that 2t has to equal negative 2s, which says that t is equal to negative s. So if t is equal to negative s, that's the first condition we get, then that implies that t squared minus 2, t is equal to, t is equal to negative s, or s is equal to negative t. Same thing. So if s is equal to negative t, they'll give you t squared minus 2t squared is equal to negative 4. And that tells you that negative t squared has to equal negative 4, which implies t has to equal 2 with a plus or minus on it. Okay? So that says that, tells us that it is possible when t is equal to plus or minus 2. So for example, when t is equal to 2, then s has to equal negative 2. Or you could have had t being negative 2 and then s would have come out to be positive 2. So here are two examples of cases where the question is satisfied. Okay, so let me come over here and sketch in green what's going on. So what we have here is that at t is equal to 2, t was where you were along the pink line, the pink curve. Okay, so at the point r of 2, since the curve was given up there at the top, 2t, t squared minus t squared, so at the point 4, 4, negative 4, okay, at that point, and r prime of 2 is equal to 2, 4, negative 4. So one of the lines, okay, L is a function of S. One of the lines for the tangent is 4, 4, negative 4 plus 2, 4, negative 4 times S. And so otherwise known as 4 plus 2S, 4 plus 4S, and negative 4 minus 4S. So if you follow this line, here's your line, for S being some time, let's say between 0 and, oh actually, looks like we have to go backward in time. Negative, if you plot that from say negative 3 to 3, when you get to S is equal to negative 2, you will intersect the point P that was given to us. Okay, so it might be a good idea to try to check this plot if possible. Here is this little Mathematica code. We can put in the curve that we were looking at. The curve was 2t, 2 times t, t squared, and negative t squared. Okay, and then the tangent line, okay, which was a function of s, was supposed to be a curve evaluated at 2 seconds plus the derivative of the curve at 2 seconds times s. And then if you plotted, okay, oh, this may be kind of hard to show. I'm going to be a little tricky here and change t to s. Okay. And if you plot this curve, t was equal to 2. I'm going to have to plot this as a function of s. Okay. We'll have to do 2 separate plots. I wish there was a quick way to do this. Okay. I'm sure there is a quick way, but I'm just not seeing it at the moment. Let's plot the curve from, if you plot the curve from say like negative 4 seconds to 4 seconds, okay, you'll get a plot, which is your curve. There's your curve. Okay, we'll hide it, and then we'll do another parametric plot, 3D, of the curve, the line as a function of s, and we know that if we plot s from negative 3 to 3, I'm putting negative 3 to 3 because negative 2 is right in between there. Okay, and we give these two plots a name, call it plot 1 and plot 2. Okay, and then you show the two plots together, plot 1 and plot 2. Okay, there's the line. Okay, the tangent line in the curve at the point t is equal to 2. If you follow this line backwards for -2 seconds, and so somewhere you're on the line at -2 seconds, you will intersect the point 0, -4, 4. Okay, so one thing we're not seeing here, axes labels, let's see if we can put X, Y, Z on there. We're not seeing which axis is which. Let me put this in the plot, P1. Axes label. So there's X, Y, Z. So when X is equal to 0, X is equal to 0, right there, -4 in the Y, right, and 4 in the Z. Huh. I should have intersected the point. Where is... Okay, that's why you do these plots, to double check. It's possible that I may need to look at something real quick. I'll pause the video and then come back and just double check my calculations over here and see if I've done something silly in the plotting command, because what I'm not seeing is the point 0 for X, -4 in the Y, and 4 in the Z. I expected to see the point that we were on the right line. I'll pause this and try to come back. Okay, we're back. All the math over here on the right is correct. I will show you what the resolution to this problem was. I added a new little piece of code here for plotting the point as a graphics 3D object, a point, and I made that point red. And then what was happening was the computer wasn't showing me the full range of the plot. It was only showing me a small portion of it. So I will take this part of the code out and hit Shift Enter, and this is what we were seeing before. Okay, so if I go back in and add this plot range command in, this will make the plot show me all the values of the plot from -10 to 10 and the X, Y, and the Z. And now we can see that we're seeing the full plot, and this line does actually intersect the point in question, and you are at that point, okay, on the line. Okay, if you look at the line at -2 seconds, you're at the point 0, -4, 0. So it was just the computer not showing us the full range of the plot. And so that would be a full solution to this problem, including the troubleshooting that had to go into it. So hopefully that helps.